Perfect. Then I want to welcome everybody to our third installment of Powering the Future. It's a webinar series that is coordinated by several EU-funded projects that deal with hybrid energy storage. And today we are focusing on the impact of the projects, on real-world impact. We have four very interesting just go over to the let me just introduce myself first. So my name is Daniel Kiesling. I work for the Bavarian Research Alliance, and we support projects that want to apply for European funding that have Bavarian partners, and we also support them in the communication and dissemination of projects. And today we will have these four projects. We will have a talk from Heaven, from SMHYLES, HIHELIOS, and Stories, and they will tell you about the real-world impact of their projects. Some guidelines. Please keep your microphones muted. There is the possibility to ask questions. For this, I would like you to use the comments section, and the questions will be answered during the end of our webinar. So there will be a Q&A session at the end of the webinar. If you have questions directed to the projects, then just write in the comments, this concerns this speaker or this project, and in the end, we will direct the questions to the corresponding speakers. So now, without further ado, I want to start with Haven. And from Haven, we have an expert from the Technical University of Denmark. It's Paul Sørensen. And Paul is a professor in wind and power integration and control at the TU Denmark. And since 1997, he is also a member of an IEC working group that is dealing with standards for test of grid connections. And since 2007, he's leader of an IEC working group for modeling of grid connections characteristics. He is appointed in January 2021 an IEEE fellow, and he was appointed a fellow for his contributions to wind power, converter control, and grid integration. Paul leads the demonstration work package in the EU Haven project. So, Paul, the floor is yours. If you can share your screen, please. Okay, and you have to unmute yourself.
Yes.
Yes.
You hear me now?
Yes, we hear you.
Good. And so now I'm in presentation mode, right? And I can move.
Yes, you are in presentation mode, and we see it full screen. It's perfect.
Yes, good. Thank you very much, Daniel. And thank you also for me having the chance to join this webinar. So on behalf of Haven, this time me. I want to first to say a few things about the concept, because in Haven we are developing the hybrid energy storage concept, and then we are demonstrating it in pilot applications. But the concept is shown here, and it consists of a hybrid storage system with a high energy battery and a high power battery. And they are connected jointly to a DC connection point, which is of course also an interesting aspect, even though we are actually supporting the AC network with the services that we are delivering here. So what we have we have cognitive power converters that are also developed in the project by Fraunhofer. Yes, let me go to the overview of the project. So we are here in the workflow now, where we are have developed or is in the process of finalizing development of the components, including the battery systems, and then they are going to be assembled and demonstrated, and that's what I'm going to mainly talk about today is what we have of plans, not what we have of results at this point, because the demonstrations are to come. Good. Then the main application that we have is to deliver. We have defined key grid services which are demonstrated in the pilots that we have made, and we have categorized them into load balancing, transmission, distribution, and end user applications. On the load balancing, we both use the battery system or the hybrid storage system to levelize and the power, so to reduce the fluctuations from the power, and we have made technical KPIs accordingly to that, but also to shave the peak power. And then we have what we call transmission services. They are traditional frequency support services, but it also includes it's quite Nordic fast frequency response. Sometimes, or it's trying to compensate for the decreasing inertia in the Nordic power system by this service. So this is the fastest service that we have. And then on the distribution side, we are demonstrating how we can help controlling the distribution voltage with battery systems. And finally, on the end user side, backup power, and also about reducing cost of electricity for the consumer by the time of use and real-time pricing services. That's also where we have put the balancing of renewable generation that we have inside the end user application. But that's maybe also clearer when we come to look at the demonstrators. We have 3 real demonstrators and a virtual demonstrator also. And the first demonstrator is in İMEKA, Turkish Antalya factory, where they are producing storage systems, and you can see from the picture the factory, of course. What is unique here, and that's actually the only case we have connected the hybrid energy storage battery here is connected to directly to an existing DC where the solar panel is already connected to. And then we have the connection to the grid here, but there is also a fast charging station included here, and that's really very much what this demonstration is about, because this fast charger will consume a very high power. So reducing the peak demand from EV charging in the grid is a major demonstrator here, and also or use case here, and also reducing the overall demand by better using the PV generation, and also balancing the renewable power. So that's very much about having a limited grid connection capacity, but then being able to maneuver within this room. The next pilot we have is office building in Lithuania, in Vilnius, and this is the Solitech demonstrator, and they also have PV, and they have geothermal pumps for the heat supply in this building. And this is, of course, only showing a part of the connection, but this is what we are going to demonstrate on that part of connection to the grid. And then we also have, in this case, we also have EV chargers and solar panels. So here we are going to demonstrate reduction of EV charger peak demand from the grid, the same as in the previous one, but also reducing the peak demand from the geothermal pumps, which is unique for this demonstration. We will also use the battery system to balance the power production from the renewables, which is in this case the PV, and then also to reduce the cost of electricity for the building by time of use application. And then the final one, which is the one that is the closest to me, is so-called hybrid power plant, which is some facility that we have built in the DTU campus in the Risø, where we are combining, that's why it's called hybrid power plant. We are combining wind, solar, and storage. And in that hybrid power plant, we will also have the hybrid storage on top of that. We will demonstrate this in a system which we will simulate in real time, a system consisting of loads and of gas, natural gas turbines, and we will demonstrate there the balancing of the renewable generation in the plant. So here we have both wind and solar together, and then we will focus also a lot on the frequency services in the system. That's the FFR and FCR and FFR. This is the European frequency services that we are going to demonstrate combined. And the FFR is realized by automatic generation, which is often used in isolated power systems. Here we will normally is used only the gas turbines, but having a renewable power plant like the hybrid power plant with battery, we will also be able to support the automatic generation control in this power system. And finally, we have a virtual pilot which will be based on the Masin multi-microgrid system that you see here, and it's virtual because we will only we will use a digital twin of the Haven system, and we will in this demonstration we will use this to simulate how the Haven system will work in that system. And here again some of the earlier demonstrations, but here we will also demonstrate the voltage support from using the battery in the distribution system. So this is the summary of the key grid services we identified in the beginning of the project, and we have been careful that we are demonstrating all of them at least in one of our pilots. I think that was on time.
Yes, it was on time. It was perfectly on time, even faster. Now you surprised me a little bit. Okay, perfect. thank you so much for this presentation and the insight of your demonstrators, how they are connected and how they are set up and work together. So, like I said, if you have any questions regarding the setup, regarding the project itself, or let's say it's a webinar about the real world impact, maybe about this, write it in the comment section and we will address it in the panel session that we will have after the 4 talks. So let me just go back to the agenda. So yes, next up will be the SMHYLES project. And for the SMHYLES project, we have here today 2 persons. One I want to introduce now because he's talking, and then the other one I will introduce in the panel session. So Eduardo, you are presenting for SMHYLES. No? Amir is presenting? Okay. Okay, it's the other way around. So I will introduce Amir now. So I want to welcome Amir Naebi. He's a power systems engineer at the Fondazione Bruno Kessler from Italy. And he holds a PhD in electrical power systems. He's a researcher at the Battery and Electrification Technologies Unit of the Center of Sustainable Energy at the FBK, the Fondazione Bruno Kessler. And they are located in Trento, Italy. His work centers on modeling, optimization, and control of power systems, microgrids, and energy storage systems. And he has a focus on advancing battery technologies and sustainable electrification solutions. And he will provide us insights into the project SMHYLES, safe, sustainable, and modular hybrid systems for long-duration energy storage and grid services. So Amir, the floor is yours. If you want to share your screen, please.
Thank you, Daniel, for the introduction. Do you have my voice? Is it clear?
Yes, I have your voice. I see the screen not in presentation mode yet. Maybe you can.
Yes. Is it okay now?
No, it's perfect.
First of all, I have to apologize for my voice because I've got this cold yesterday and I'm presenting it with this voice. Let's jump into the slides. We are presenting SMHYLES project, safe and sustainable and modular hybrid systems. The project started in January 2024 and ends in December 2027. We have EU funding of 60 million euros, and we are targeting TRL 7. SMHYLES is for designing for the design, construction, and demonstration of hybrid energy storage systems based on low CRM, which is the critical raw material storage technologies. That's why we have focused on aqueous hybrid energy storage systems, which is the vanadium redox flow battery plus nickel, the aqueous supercapacitor and cadmium supercapacitors. We have a salt-based HESS, which comprised of sodium nickel chloride, salt battery plus supercapacitor. We are studying and demonstrating of HESS retrofitting and storage expansions. We are developing digital twins for the HESS systems. And also we are building and demonstrating smart EMS energy management systems for the overall system, for the entire system. Also, we have some kind of technologies in the project that I'll be presenting it later. We have consortium, we have a consortium comprised of 16 partners, 5 from European countries, Italy, Portugal, Germany, Spain, and Czech, and the others from Switzerland and Tunisia. We have storage technologies manufacturers, operators and one PCS power conversion system manufacturer and universities and operators and all the other companies that are contributing to this project. We have several work packages in this project. Work package 1, project coordination and management, that we are taking care of that. Work package 2, LCA and techno-economics of HESS exploiting digital tools. And work package 3 is the design and development. Work package 4, design, integration, and optimal management. 5, pilot validation and demonstration that we will have in the coming years. And we have work package 6, explanation and business planning, exploitation and dissemination. We have 3 steps in this project so far. We have done optimal sizing and use cases. We have done technical role supercapacitors and 8 frequency regulation. We have defined that we have a supercapacitor that would help the system to mitigate the fast power changes that leads to a bit of unwanted consequences, unwanted events in the system. And we have economic insights in the project, that we evaluate the profitability of the project, that even it is profitable to install this kind of storage in the system or not. We've done all these things in the project so far. And we also have developed some models for vanadium redox flow battery and Zebra battery, which is the sodium nickel chloride battery, and supercapacitors. We have done some experiments to extract their parameters from the data and validate those parameters in the softwares like Python and OpenModelica. These models will be integrated into some energy management systems and digital twins in the end, to be used in real hardware tools, to be integrated in the real the packages and real batteries, real things in the project. As I mentioned, we have simulated 2 VRFB plus SCKs, which we call it AHESS, aqueous energy storage systems, and the other one SHESS, which is the Zebra plus supercapacitor. We have developed all these models in OpenModelica, which is a strong software for simulating the dynamic behavior of batteries and supercapacitors and power system components. Then we have the energy management system design. Because of the time restriction, I'm going so fast to cover all these points and to give you an overview of the project. This is the EMS logic we have developed for our microgrid system, that we are going to simulate and model the battery and supercapacitors. We have temperature check, battery SLC checks. We have all the power and the frequency checks inside the microgrid, and then this EMS system will command the supercapacitor or the batteries to act immediately when something happens in the system. As you can see, we have some results from the Modelica models. As a result, that VRFB maintains a flatter voltage profile and a smoother SLC evolution because it's a long duration energy storage system, and we can have a good voltage profile. We can expect a good voltage profile from this kind of batteries. It makes it well suited for long duration energy support and frequency cycling, as we mentioned in the slide. The SC again covering high frequency transients. That's why we are evaluating the system to evaluate and validate if our long duration energy storage can work along with the supercapacitor and cover the whole system's needs in each time step. Here we have 3 demo sites that we are going to implement and install our batteries and supercapacitors in these demo sites. And the first one is Sonai campus in Portugal. The case study is tracking active and reactive power targets and evaluate the performance of control loops we have developed in softwares like Dixilent, and the performance of voltage reactive power control loops. The other one, the demo 2 is Graciosa Island, which is an off-grid island operated by their operators, a private operator. The case studies we are following in it work in this demo side is WPP loss. For example, they have wind parks. So what would happen if we lose this wind park and the system remains stable or not? This is the question that we are going to answer in our simulations. And also we have short circuit analysis that how these hybrid energy storage systems would respond to these transient faults, and also how would the conversion systems would react to these FRT during faults, because they are so essential. It's an islanded microgrid, so we would have this kind of transients in the microgrid happening, and we would need reliable and good power conversion systems. Also, we have demo site number 3, which is ICT Fraunhofer microgrid in Germany. So the case studies performed are the comparative analysis of key performance indicators, or KPIs, for renewables, because it's a retrofitting project, and it's like we are adding to their microgrid the VRFB tanks. We are extending and expanding their microgrid that is operational microgrid, which is an interesting case study. This is just a simulation for demo number 2. We have this microgrid in here. We have the HESS system, supercapacitor, and the batteries connected to their already operating bus. And these kind of simulations have done on the real microgrid with real condition. And as you can see, the supercapacitor plus battery help the frequency to recover more faster and better. We have less power generation fluctuations, and we have good frequency responses. These are just 2 images representing the frequency response. We have all other simulations carried out on this microgrid. And that's it. And we have the conclusion and remarks part. We are going to validate if this hybrid energy storage system, batteries plus supercapacitors, can be coupled to power systems and can help them to decouple energy and fast transients. If they can provide fast transient support to the system or not. And we are going to use digital twins in our system by using tools like OpenModelK and Dixilent, because they're crucial for optimizing our control strategies we already built. We are going to evaluate the economic reality of the system, which is also important for the European Union projects. While technical performance is good and high, economic viability depends heavily on market structure that we also reviewed in our deliverables, that if it is profitable to use this system or not. Also, one of the aspects that the SMHYLES project has focused on is at the low CRM technologies, because we are going to study if these critical raw material technologies are viable, if they are safe for replacing lithium-ion or for long-duration energy storage systems, to lower the dependency on the lithium batteries. And our next step would be to move from simulations to physical operations, because we are targeting TRL 7. at the 3 pilot sites that we are going to, we are having meetings among partners to for this demonstration phase. And we have future regulatory frameworks that should be reward these technologies, that should help these technologies to thrive, to be more prevalent in the future, and we are working towards this goal. And I'm sorry if that took a little bit too much.
Yes, it's fine. I let you talk because it was a very, let's say, detailed insight, but I think there was also a lot of very interesting information. Sorry, Paul, I was thinking somehow 15 minutes, but we agreed to 10 minutes. So Paul was on time. You took a little bit too long, but it's okay. I think we can manage. But now I want to go on to the next project. And like I said, any questions, please in the chat. Now I want to go to the next presentation, which is the HIHELIOS project. The HIHELIOS, a high energy, high power hybrid battery storage solutions platform for multiple grid services. And for that, I want to welcome Mohsen Akbarzadeh. And he is a business developer and at the same time a battery systems specialist at Flanders Make. And he holds a PhD in battery systems engineering. And he comes with extensive experience in developing and implementing battery-related projects across diverse applications. Throughout his career, he has contributed to numerous European projects in the battery sector. And they were encompassing electric vehicles, stationary energy storage, and maritime applications. Now, please, Mohsen, share your screen and you can start with your presentation.
Okay, thank you very much. Hello and good afternoon. So I'm going to present a HIHELIOS project. First of all, a quick, let's say, overview of HIHELIOS. As you mentioned, it stands for demonstrating a high energy and high power hybrid battery storage solutions platform for multiple grid services. It is Innovation Action Project, and we kicked off almost 1 year ago in December 24, and the project will last for 42 months. The budget granted for this project is around 6 million euro, and the project is coordinated by CA. Within our consortium, we have 12 partners from 5 European countries and 1 country from Africa. We pursue 2 major goals in HIHELIOS. The first one is design and develop a modular and highly safe, sustainable, and cost-optimal electrochemical hybrid energy storage system that can be adapted to various grid applications. Our hybrid battery, electrochemical hybrid battery energy storage system, is based on the integration of multiple lithium-ion batteries in terms of chemistry and in terms of lifetime. We also try to reduce the reliance on critical raw materials by optimal selection of our battery technologies and other components. We are aiming to develop let's say, control system which is interoperable, scalable, and robust with a multi-layer coordination system and built-in cybersecurity. The control system also will be equipped with advanced fault diagnostics and predictive maintenance, which is enabled by physics-based and data-driven battery models. The second, let's say, major goal is to demonstrate this hybrid energy storage system, for which we are aiming to demonstrate our solutions in 3 European countries for different use cases, which include EV smart charging, EV fast charging, non-interconnected grid, and a marginal load supplying system. We will demonstrate the solution in 3 countries, including Norway, Belgium, and Greece. So in HIHELIOS, we will cover north, west, and south of Europe. And the target is to, let's say, deploy more than 1 megawatt hour hybrid battery in total. Why hybridization of lithium-ion batteries? There are multiple reasons for that. One of the important aspect is balancing energy and power requirements. As you can see on the left, the current lithium-ion battery technologies are either high power or high energy. So if we go for higher energy, we will sacrifice power and vice versa. So when you have an application with variable load cycles, sometimes it needs high energy, sometimes high power. If we use a single chemistry, we might end up with an oversized battery system. Therefore, here we propose to combine different technologies, high power and high energy batteries. So by this solution, we can avoid oversizing of the battery. For example, if we only use a high energy battery for a certain application that sometimes needs high power peaks, we might come up with an oversized battery in terms of power. If we use high power battery, also you can see on the right figure, we will come with oversized in terms of energy, and hybridization can potentially, let's say, lead to the optimal sized battery system. Another aspect for hybridization is balancing lifetime and potential, let's say, reduction of the size from the lifetime point of view. In this regard, I would like to give a quantitative illustration. On the left side, you can see the cycle life of three common lithium-ion technologies, NMC in blue, LTO in red, and LFP in yellow. Here you see the impact of depth of discharge on the cycle life. Let's suppose we have an application that requires 6,000 cycles. To meet this number of cycle life, with NMC, we need 70% DOD, and with LFP, we need 90% DOD. Also, let's assume that our application needs 400 kilowatt hour energy. If we use a single chemistry like NMC, so the usable energy, as mentioned, is 400 kilowatt hour, and our DOD is 70%. We need to install 570 kilowatt hour NMC to meet these requirements. On the other hand, if we choose a hybrid topology and combine NMC and LFP, we can take 175 kilowatt hour out of this 400 by NMC, and the rest 225 from LFP. With the mentioned DODs, we need to install 250 kilowatt hour for each of these technologies, and the combination will be 500 kilowatt hour. So by hybridization, we are able to reduce more than 12% the size of the battery system due to the better lifetime balancing. Therefore, I would say in the sizing of this hybrid energy storage system with lithium-ion battery technologies, there are multiple parameters involved, like the energy, power density of the batteries, lifetime, and even more parameters like thermal behavior and so on. So optimal sizing seems to be, let's say, a complex exercise. That's why in HIHELIOS we have used an advanced battery sizing tool, which was developed by Flanders Make. And we previously used this tool in another project named CBAT, where we studied hybrid batteries for maritime application. And we adapted and, let's say, updated this tool in HIHELIOS to use it for grid applications. And this was the first step in the project to find the optimal size of this hybrid energy storage for each use case. Using such tools, sizing tools brings multiple benefits. We will know the optimal share of each battery chemistry to meet the, let's say, performance and cost targets of any application. And we can ensure the right size battery capacity is, let's say, used for the real world operation. And this will avoid higher capex by avoiding the oversized battery, and also it ensures that we can meet the lifetime and performance targets. Such tools can support decision makers and project developers for different demonstration sites because each application has its unique load cycles, operational constraints, grid conditions, and so on. And also, we can reduce the technical and financial risk by simulating the battery degradation behavior and operational strategies before we go for the on-site deployment. You can see some screenshots of this tool. We can select the architecture for the battery, either use the classic or monotype battery or a hybrid battery. We need to import representative load cycles from the application. We will define the specification of the battery, energy, power, also the operating state of charge, and so on. And at the end, the tool will optimize the system and give us the optimal values. And also it compares this with the monotype, let's say, system in terms of cost, weight, and volume. In terms of sustainability and circularity, the main chemistry in HIHELIOS is second life NMC. And why we chose this, there are multiple reasons. First of all, I would say that the previous generation of EVs in Europe are mainly using NMC technology. And nowadays and in the future, we expect a lot of second life NMC from the EV market. Also, some research studies show that the market for second life EV battery will significantly increase after 2030, as you can see here. Also, NMC contains, let's say, valuable materials like nickel, like cobalt, which are associated with the limited global supply. These are also, let's say, associated with environmental and social risk, and also energy intensive for mining. By using second life NMC, we will delay recycling, and also we will maximize the, let's say, extraction value. So we chose NMC as the main technology, and depending on the application and its requirements, we will combine it with first life LFP or LTO to balance the lifetime or power, let's say, requirements. And in general, this concept where we use second life NMC will cut the demand for new materials and reduces the environmental impact. It also boosts, let's say, resource efficiency because we have both first life and second life batteries in our concept. Also, the concept aligns very well with the circular economy principles. And another major, let's say, impact will be that we would like to prove the viability and feasibility of using second life and repurposed batteries combined with other chemistries as a hybrid storage system for real applications. Also, we have one, let's say, advanced control system to be developed in HIHELIOS, which has a multi-layer architecture. We have a battery management system, we have power management and energy management system. Energy management will optimize the operation of the local assets. The BMS is in charge of monitoring of the battery status and some safety functions. And we have something else named PMS, Power Management System, which is in charge of optimal split of the power between the two different battery types that we have. And with this multi-layer system, we ensure safe, resilient, and let's say high performance, let's say, coordination of the communication between the different layers. And by optimal split of the power between the different batteries based on the, let's say, specification of each battery in terms of, let's say, C-rate, thermal limitations, energy, lifetime, and so on. Let's say this control system ensures maximized efficiency and safety. Also, we have here, let's say, advanced monitoring platform based on physics-based and data-driven battery models for monitoring of the state of health, fault detection, and predictive maintenance to reduce the operational losses and enhance the cycle life. Especially for second life NMC, this is very important because the second life battery is more associated with the safety risks compared to a first life battery. And also we have, let's say, secured edge and cloud layers to have seamless communication with external stakeholders like utilities, aggregators, and so on, in order to have a flexible control framework, and we can, let's say, apply this control system to different application on different sites. Here you see an example just based on a DC link, but this concept can be applied to an AC link as well. And my last slide is about the use cases of HIHELIOS, where we want to, let's say, demonstrate these solutions. The first one is a smart EV charger in Belgium. And I would say that this smart EV charging aims to meet the mobility requirements of the users who park their vehicles in the area. There is also a PV system there, and battery, the HIHELIOS battery will be integrated there to enhance the performance of this PV, and also users will be able to charge their vehicles at a low price. The second use case is a EV fast charger, a megawatt charging system, and HIHELIOS, let's say, energy storage, hybrid energy storage will support the grid connection power limitations for this use case. The third one is non-interconnected grid. This is located in Greece. There are several islands with this non-interconnected grid. Our demo will be in Tilos Island, which is the last island here, which faces some limitations and weaknesses in terms of this non-interconnected grid. That's why the DSO there has implemented a hybrid power station, and the HIHELIOS solution will be connected there in order to, let's say, increase the storage capacity of the hybrid power station, and also to enhance the operational performance. And the last one, also in Greece, is a marina load supplying. It's a microgrid with PV, and also HIHELIOS battery will be integrated here. There are multiple applications here, like a EV charger, boat charger, and also marina building and lighting system. And the HIHELIOS hybrid energy storage system will be demonstrated for this use case to improve the, let's say, performance of this microgrid as well. Thank you very much.
Okay, perfect. Thank you, Mohsen, for this very, let's say, hands-on presentation, in a sense that you presented tools that are applicable to real life impact with the modulation and the suggestions that you can then make with the tools. And I'm really looking forward for the discussions. So I'm aware that we are a little bit behind in schedule, but I think that's okay. It was up to now all very interesting information for the discussion that we also need to have a more in-depth discussion. And now I want to introduce you to Miriam. She is representing the STORIES project. STORIES, Storage Research Infrastructure Ecosystems, is a project that is now ending, unfortunately. So have a look out for the last or the final deliverables and presentations and publications also. I think one of the major publications is already online, but maybe you will also say something about that. Miriam is team leader, international joint projects at the KIT in Karlsruhe. She's a senior research manager and business developer there. She studied chemistry at the University of Zaragoza and received her PhD in supramolecular chemistry by the TU Dortmund. And now she has been working in the field of energy storage for almost 20 years. She's actively participated in more than 10 European projects on energy storage, and 3 of them as a co-coordinator, so supporting the coordinator. And currently she is also in the storage projects co-coordinating. She's editor of an open access book on hybrid energy storage, case studies for the energy transition. So you might want to check out this one. And she has authored several peer-reviewed publications, also the EASE ERA Energy Storage Technology Development Roadmap. So you, Miriam, the floor is yours, and please, if you can share your screen.
I'm not sharing now.
Yes, yeah, no, it's working.
It's working?
Perfect. I had to end mine. That's okay.
Okay, thank you very much. So if I'm too long, just let me know. So thank you very much for this kind introduction. Let me start showing you this picture. As you know, on April 2025, the entire electrical system of Spain and Portugal shut down. So this was one of the most significant blackouts in the history of the European grid. And as you know, this unfortunate event highlighted, among other issues, the need for energy storage. For example, to ensure grid stability. And this is something that I always like to show, because the need of energy storage is there, and we need always to talk about that. Okay, so this is the storage project. Let me spend a few words on that. So as you mentioned, the project started in 2021 and ended last October. We had 7 million euros. The consortium was composed of more than 47 beneficiaries, and this is a research infrastructure project. So one of the aims of this project was to provide access to the infrastructures. And we were able to gather 64 research infrastructure covering all fields of energy storage technologies. So electrochemical energy storage, chemical energy storage, thermal energy storage, and mechanical energy storage. So the project consists of 7 work packages, as you can see here. The first one and the main work package 1, is about building an energy storage ecosystem. Work package 2 is providing access to the research infrastructures. Work package 3 provides different services that I will briefly show you now. Work package 4 is dealing with sustainability and techno-economic aspect of energy storage. And finally, work package 5 dealing with dissemination, exploitation. Work package 6 and 7 with coordination and management. And the main outcomes of the different work packages, as you can see here, in work package 1, we have a lot of experts working in different working groups, and we were able to build an ecosystem composed of more than 250 organizations, stakeholder organizations, and experts that were involved in the project activities. And also we provide a white paper on open data for the energy storage community. As terms of research infrastructure, we were able to open 7 transnational and virtual access calls, providing more than 300 access weeks, which is a lot. And work package 3, for example, in this case, we provided services, and we established a material acceleration platform for hybrid energy storage. We developed a technology roadmap and a book complementing the roadmap, as well as a strategic research and innovation agenda for hybrid energy storage. And this is what I would like to show you today. So among these, we also had an education and training program. You can see here, organizing summer schools, mentoring program, online course, a lot of work also for early stage researchers. And we also published a white paper for sustainability of hybrid energy storage systems. And finally, of course, exploitation roadmap. So, but what will the future energy system look like? First, we need to consider that the future energy system will be much more decentralized, integrated, and highly dynamic, including the integration of multiple energy carriers such as electricity, fuels, hydrogen, and heat. And the interoperability across energy carriers, vectors, and scales will define the system resiliency, efficiency, and sustainability. And for this, we will need hybrid energy storage. Because hybrid energy storage combine multiple storage types, not only batteries. In our case, we try to combine all the energy storage technologies depending on the application. So we look into the application and then we look into the technology that we have available, and we try to find storage solutions that are much better or have better performance than the single technologies. Hybrid energy storage also balances across different time frames, from milliseconds to years, if necessary, for seasonal storage, supports sector coupling and cross-vector energy flows, enables self-risk taking, and finally strengthens also system resiliency in low inertia grids, for example. But what is clear is that there is no silver bullet solution. There is no single technology that can solve all these challenges. Rather, a combination of different technologies is needed. And this is exactly what the STORIES project is about. STORIES is a research infrastructure project gathering all kinds of energy storage technologies under one roof. And within the STORIES project, we develop a technology roadmap for hybridization of the different storage technologies, which define the need for energy storage across stationary and mobile application, as well as technical challenges. And complementing this roadmap, we also identified 17 real-world case studies on hybrid energy storage systems, which have been included in this open access book. And finally, we develop a strategic research and innovation agenda highlighting the research and innovation priorities and strategic research areas in the field of hybrid energy storage across Europe. And I would like to show you now very briefly. Here you can see the structure of the roadmap. If you scan the QR code on the left-hand side, you will access this document directly. Now I won't go very much into detail. I just wanted to highlight that hybridization means combining two or more energy storage technologies to work together to deliver better performance, to offer flexibility, to store energy on different time scales, and at the same time are much more efficient and economical than existing storage solutions. And we can make hybridization at different levels. We can do it at material level, at device level by combining different devices, or even at system level. And also we spend a lot of time trying to find a proper definition for hybridization, because this is a bit tricky. Everyone understands hybridization in a different way. So if you are interested, you can have a look into the document and you will find this definition that we propose. So this is the book. Also, it's an open access book and we're very well welcomed by the community. It was released 2 months ago and has been downloaded more than 40,000 times. So I think it's very interesting. And this was a joint effort between the ERA Joint Program on Energy Storage and the STORIES project. In this book, we identify and develop 17 case studies to illustrate the application of hybrid energy storage across different sectors, including industry, grid services, off-grid systems, transportation, and buildings. And I will like to show you now very briefly. So here you can see all 17 use cases, depending on the sector. Let me show you one by one. So in the case of industry, we identified these 3 case studies. The first one is mid to long duration. It's about industrial applications of high temperature heat and electricity storage for process efficiency and power to heat to power grid integration. The second case study is very interesting. It's about repurposing retired fossil plants, combining second life use of batteries with integrated flywheels and high temperature molten salt storage. The case study number 3 is about optimizing renewable power system by using hybrid gravity storage with batteries for wind and PV integration and load balancing. For grid service, we have identified these 3 different case studies. The first one is the integration of run-of-river pumper hydro with an energy storage system based on batteries and supercapacitors for enable ancillary services, and of course, extending the lifetime of the equipment. Case study number 5 is about power-intensive energy storage systems. And case study number 6 is about hybrid energy storage systems coupled with renewable power plants for power smoothing applications. In the case of off-grid systems, you can see here we oriented into the different geographical situation. The case study number 7 is about Northern Europe and Arctic region. In this case, this is a use case on hybrid heat, power, and storage solutions for comprehensive farm energy needs that are off the grid. Case study number 8 is about southern climate, integrating batteries and reversible heat pumps for cooling and supplying electrical load. And case study number 9 is a geographically adaptive use case. In the case of transport, we have defined 5 different case studies, as you can see here. Case study number 10 is about charging infrastructure using hybrid energy storage system for integration and charge management of EV charging stations. And the remaining 4 case studies within this sector are addressing different transport, from waterborne to rail transport, airborne transport, and heavy-duty road transport. If you are interested in one of these specific use cases, you can just scan the QR code on the top and you will find all the data on all the technologies involved in the different case studies there. And finally, the last sector that we address in the book is the smart buildings. And for this, we also define 3 different case studies depending on the buildings. The first one is covering small buildings, single-family homes, combining phase change materials, batteries, vehicle-to-home-to-vehicle system for combining the storage. Case study number 16 is about larger buildings like office buildings, in this case more than 50 kilowatt-hour per day, integrating batteries and phase change materials for peak shaving and load management. And the final case study is a combination of lithium-ion batteries and organic redox flow batteries for behind-the-meter applications. So on the last slide that I would like to show you very briefly is the SRIA, this strategic research and innovation agenda that we developed within this project. You also can see the full document under this QR code. And in this case, we define 4 different strategic research areas that we consider need more efforts in research for the further deployment of hybrid energy storage system. And also we made 13 policy recommendations at both European and national level how to cope the barriers and challenges that are now there and that are avoiding the deployment of hybrid energy systems. So this is all from my side. Thank you very much for your attention. And if you have any question, I will be very happy to reply to you. Thank you.
Perfect. Miriam Il-Badahi, thank you for the presentation. So, like I announced in the beginning of our webinar, we have 2 parts of this webinar. So one is the presentation by the projects themselves. Now we are going to a discussion or a panel session. And for this, I want to introduce 2 more persons, and I do this in the order how the agenda was structured. So I will start with one additional SMHYLES representative, the coordinator of SMHYLES, Eduardo Gino Macchi, and he's the head of the Battery and Electrification Technologies Unit of the Center for Sustainable Energy at Fondazione Bruno Kessler. And he has an engineering background, and he was able to acquire a wide range of competences covering mathematical modeling, engineering and testing of electrochemical devices and energy systems. And since 2018, he's been in charge of the battery R&D activities at FBK. He is responsible for FBK's project within the EPSA, European Battery Innovation, and he is also a link to the BAT4EU partnership, where he's actively contributing to several working groups, in particular new and emerging battery technologies and the working group on stationary applications and integration. And then I want also welcome Yves-Marie Bourien. He's research engineer in stationary storage technologies at CEA in France. He's working for more than 15 years on stationary storage technologies, mainly batteries, and batteries for providing ancillary services, flexibilities, and for easing renewable energy integration at different grid scales. So hybrid systems, microgrid, CI grid, electrical network. And since 15 years, he's working at CA on several topics: performance and security testing and characterization of battery technologies, sizing and modeling of BESS systems, self-consumption, grid flexibilities, and second life applications. So welcome both of you to the panel. And I think I will stop share the screen, because then we see each other better. Welcome all. So now we have more or less not half an hour, but almost half an hour to discuss. I want to start with questions that we got. So the questions are directed to projects, and then we will have an overall discussion. And I also want to encourage you, if you then have questions as a panelist, maybe also to the other projects, maybe you also want to ask something. And I want to start with the HEVEN project, and this question goes to Paul. And the question was the applications that HEVEN is dealing with. What applications would you see have the most impact or the most promising results in relation to your technologies? And you're still muted, sorry.
Now I'm not muted, right? You hear me?
Yes.
Thank you. I think there is one general, so to say, line in the applications is that the grid needs, because of the transition of the electrical energy grid, it really needs to have flexible support, also on different time scales. So I believe that this is very much as what has also been said already, one way or another, that between very fast power injection and also energy injection, even on seasonal scales, we have heard here. But I think it depends very much also on the type of system we are in. When we are in the large interconnected systems, we are still, the main struggle is still on the balancing of power to generate when we need the power, and there the storage system is very helpful. But then, as was also mentioned, another important part is to actually be able to keep a stable grid operation. And that often requires more fast response. So I would not pick a favorite in my answer, but rather say that I think that supporting the grid, and also this is also coming out as a benefit for the owner, of course, because there is a high value for the grid, that when we have much renewable generation in the grid, that we are not need to run thermal plants at the same time in order to have reserves in the network.
Okay, so you would say the grid applications, the grid providers would potentially benefit from the solutions, from the technologies.
Yeah, and that can come back to the owners also, of course, by payment for services.
Yes. Okay, perfect. I have a question for SMHYLES. And there, Amir, you talked about digital twins. There was a work package also on this, dealing specifically with this topic. And the question would be, so there is the energy management system and you have the digital twins. How do they interconnect? How do they work together? And what's the advantage there?
As I mentioned during my presentation, the digital twin is like a digital representation of the real system before any deployment. Before you have the actual system, you have this digital twin running in a virtual environment, and you can implement some kind of optimization algorithms in it to optimize the system's overall behavior or some kind of risks that the system would face in future operational times. For instance, in our Graciolica island that I presented, it's an offline grid, it's an islanded grid. So we have to take all the risks into account that whether this kind of fault would happen or loss of a wind power plant, wind production or PV production would cause any kind of things in the system. So we need this digital twin, as the other projects have implemented some kind of digital twins in their system. And then we have this energy management system that can be integrated into this to help us, as I mentioned, mitigate the risks of real deployments. And also it would help us to do the optimizations, energy management, which is so important nowadays, and because we should increase the efficiency of the system with this one. So our main focus is to implement a good digital twin that is fast enough, and also on the other side is detailed, not just a brief representation of the system. We need accuracy and that this kind of being fast, because we are going to implement it in software tools.
Okay, so just for my understanding, if I got this right, you use the virtual digital twin system for planning, but also for during operation, for optimization and.
Yes, it's like you have the real system out there. You create a digital shadow, a digital representation of the system. You have the batteries models all inside the digital twin. And then you start doing a simulation with that digital twin system to see what would happen in cases. In some cases you define that some cases that may happen in the future, and then you are preparing your system to face these challenges for the future with this digital twin system. And then it would have some EMS, some optimization algorithms inside it that you can do everything in it.
Okay, Miriam, you had a question related to that? No? I'm sorry. I thought you unmuted yourself. Okay, no, it's fine. Thank you, Amir. Perfect. Now, coming to HIHELIOS, there was the question about what type of grid services HIHELIOS will be testing with its hybrid systems. Is there any kind of specification there?
Actually, I briefly introduced the use cases that we will demonstrate our battery in my presentation, but maybe to have more, let's say, overview on the details and the type of grid services, since we have the coordinator of HIHELIOS, Yves-Marie, on board, and he can probably give a better answer because he's more in contact with the demonstrators and the stakeholders. So, Yves-Marie, if you can maybe you reply to this question for HIHELIOS.
Yeah, Thank you, Moshen. As explained by Moshen during the presentation, we are at the end of the first year of the project. So the work on the first year was on sizing and defining the use case. We know since the beginning of the project the location of the use case, but we work on the definition of which real needs the stakeholder have, and then to design the system and to size the system for these needs, and not the reverse, and to adapt the needs to the stakeholders. We really start from the needs from the stakeholders, and we have different use cases as explained by Moshen. The first one in Norway for fast charging is really on peak shaving, regarding the cost of the peak shaving. And also it can deliver some grid services if needed in these locations. And above the peak shaving cost, there is also the energy cost. So there is some arbitrage service for this use case. Really grid connected use case. The Belgium one is more on, let's say, office and commercial locations. So it's more on self-consumptions, but it is a lot with vehicle EV chargings. And the aim is not to increase too much connection to the net electrical grid, even if we increase the number of EV charging slots combined with PV production. So we have arbitrage, we have, let's say, decrease of the peak demand from the grid, and we have self-consumption. And for the two other use case, it's on Telos Island, so it's more on it's more focused on non-interconnected grid and low inertia grids. The smart marina use case is really at the end of an electrical line, so it's for voltage regulations, voltage support to decrease as much as possible the power consumptions and the power injection to the grid from the PV. So we have some consumption arbitrage and this kind of congestion. And the other one is located at the, let's say, electricity grid core network of the islands. And it aims to support the current existing storage systems that we have in Telos. So it's from a former European projects. And in case of disconnection to the all other islands, this system should support the current one by providing more energy, but also by providing more power with black start capability and more stability. And that's it.
Okay. In these demonstrators, where you have a look also at the EV charging, are they then bidirectional, the EV chargers? Can you use that, or
no, for the moment
not yet?
the one in Norway is really for fast charging, so bidirectional is no sense in this point of view. But for the Belgium case, it could be bidirectional, but as there is it's real system with real cars, and as there is very low number of models of EV that are currently bidirectionals, we just have like a smart charging options, which is still a very high level of flexibility that is not used for the moment.
Yes. Okay, but the goal is to optimize the usage of the produced energy, of the self-produced energy, and not to use the grid electricity, right?
Yeah,
this is the service, so to speak.
Yeah, and not to oversize the connection to the grid for the EV charging needs in terms of power. Yeah.
Okay, perfect. Thank you. Thank you for that answer. So I have one question for the Stories project. We heard that the Stories was an infrastructure project. This is also about services that these infrastructures provide. There is a connection to the industry, most likely. So one question would be, how do you connect then, let's say, not theoretically, but practically, the researchers and the industry? And will that continue once the project, well, now it's ending, so how will that continue?
Yeah, well, thank you for the question. Indeed, one of the main goals of the storage project was to create an European ecosystem of both industry and research organizations working together on hybrid energy storage technologies to develop new concepts on improving performance of storage devices, to make them more competitive and more cost efficient. So for this, we put a lot of efforts and organizing workshops, webinars, outreach to member state representatives, for example, also to policymakers, involving all of them, industry also, involving all of them in these webinars, in the working groups that I have showed you at the beginning. We had different working groups addressing different topics. And we managed to got this large ecosystem of more than 250 entities, which is really impressive. And now the project had ends, and of course we will keep working on hybrid energy storage within other frameworks. For example, the European Energy Research Alliance, that is also that is composed of different joint programs. One of them dealing with hybrid or with energy storage. And also the members, the consortium partners sign a memorandum of understanding to keep working together, because we think this is a very important topic that need to be further developed.
But will you keep the name or the brand Stories? Because this sounds pretty much like a cluster that you formed there. And I think the partners, they have stories in mind when they cluster with this network. So will that be living on in one way or the other? The branding?
Actually, we were looking for different calls as follow-up project. Indeed, the point is that we couldn't find a proper call that's just to have a second phase of this project, exactly the same, our research infrastructure project, providing access.
Yes.
But we succeed to submit a proposal for another call, and in this case, we'll be dealing with energy storage, hybrid energy storage, but with the support of artificial intelligence. It will be very similar as was mentioned before. We will develop different digital twins for long-term and long-duration energy storage, and this will be a kind of follow-up project, but not exactly the same, but we have some ideas already how to proceed with this. Yes.
So it will not be stories, it will be store AIs, right?
Actually, the other way around, AI stories.
AI stories.
But
Okay,
it's not
nice.
yet granted. It's a proposal that we submitted in September, so we hope the best.
So if there is an evaluator listening,
yeah, exactly.
It's AI stories. Have a look in your inbox. Okay. Yeah, that sounds very promising. Okay. Great. Now I have a question for all the projects, because I mean, we talked about impact, but a lot of the solutions, they were data-based, right? So we have these tools that Mohsen presented. We have the digital twins. We have the users that Stories had a look at, right? So, but to my understanding, you need data, and also now with the AI coming up, you need data. You need data to learn your tools, or Mohsen said if they want to have this optimization tool that recommends a certain configuration, you need to insert load profiles. But you want to install the system, right? So where do you get the load profiles from? Now, my question would be, how open, and this goes now to all the projects, how open are your publications, and especially the data that is behind, and also the tool that Mohsen showed? I mean, Miriam, you already said you had a lot of open access publications. Is there also the data included in a way? Load profiles, measuring, sensor data, whatever. So I don't know how we, who wants to answer first? There's a show fan. So Ismail, please.
Yes, for HIHELIOS, the tool that was shown by Mohsen was developed in a former project, and it's available free to use. You can use it also for another project. And for the data generated, it's sure that it's always a difficult point to size a system that does not exist for new applications. So you have to create data or to have reliable data for the use case that are not existing for the moment. So for Telos, we based on some data existing from the former Euro project and also for the current situation of the grid that we want to improve, and we make some hypotheses and we have some margin in the sizing. And for the Norwegian use case for the fast charging, we have developed a EV schedule simulator, so that can simulate the arrival of EV based on the traffic of the roads, and we evaluate this simulator based on data for another EV fast charging stations in the same country. So just to compare if it's reliable data or not. But these data are maybe not available after the project, but the data from the demonstration will be certainly available after the project. But we have to wait 2 years.
Mm-hmm. Yes. Okay.
Also, just a short note about the sizing tool. It is intended to optimally size a hybrid battery storage system. So for any application, either stationary, mobility, maritime, whatever, if there's already a load profile from the existing battery, we can use it and see if we go to a hybrid solution, how much weight we can reduce, how much the cost will be improved. So one of the usage of this toolbox is to study combination of different batteries, replacing an existing battery storage system with monotype configuration.
Okay, perfect. Amir, Eduardo, anything from SMHYLES? Open data? I don't know.
Yes, I can take this one maybe. So yes, data is for sure crucial, but sometimes it's also critical because, I mean, while if we base our system on something using AI, having data, and also for designing, of course, having data is crucial. Sometimes data cannot be public. I mean, just yesterday I was in a meeting where we were discussing about AI for the power system, and all the TSO, of course, were saying, okay, but we cannot share all our data with everybody. So that's one point that is tricky. On the other side, I think frequently, I mean, in the project, we have partners that are willing to share the data, and that can be useful, of course, to build tools. For example, one for sizing that we also have in SMHYLES. Other tools, the one that Amir presented regarding the energy management. Some of these, let's say, in the coming months, most likely will be open, and some of the results will be public. Maybe not everything, because of course there are also constraints regarding the sensitivity of the data and the sensitivity of the results. But I think, I mean, open science in general is quite an important point for the Commission, but also to allow, let's say, a use of what we are producing within the project. And although, of course, we know that not everything can be made public, but I think that that's also a good advantage to try to use results and improve them instead of just duplicating them.
Yeah, absolutely. I mean, not duplicating, not doing the work double. Paul, you also have a comment?
Yeah, I will not talk on behalf of the other demonstrators because I'm not very sure if I say something wrong, but I can say for the hybrid power plant, we are definitely planning to share operational data from wind and solar and storage operation together. And we also have in DTU a simulation tool for wind and solar generation, which we have been used also in the design phases and shared with our partners. So we were able to have some initial values because when the project started, we didn't have really the measurements that we would like to have. when we were designing the energy management system.
Okay. Well, maybe this could be a starting point for further collaborations between the projects. I'm looking at the coordinators and yeah, so maybe some not working group, but just initial discussion if there is a collaboration possible. I mean, the projects are, some of them are still running, stories unfortunately not, but then with the new projects, with the AI stories project, so that could be a nice collaboration there. And I would encourage you to connect and also talk after this webinar. The webinar itself will close now. We are perfectly on time. It's 15:30, and I want to thank all of you for your contributions. I think it was a very good discussion. We learned a lot of things. The presentations, they will be available to everybody participating in the webinar. And yeah, let's see what please keep an eye open for future installments of our webinar. We will have a different focus for the next time. We don't know yet which one, but we will inform you in time. And I would be happy to invite you or to welcome you to further installments of our webinar. Then thank you. Have a nice evening, afternoon, and goodbye.